In order to go into more detail about what's happening in the structure of the molecule, we need to pause for a second or take a step back and talk about something called bond polarity. We've been drawing a lot of Lewis structures, and so I'm going to draw a couple very quickly. For example, the Lewis structure for the HCl molecule would look like this with all the lone pairs. The Lewis structure for the H2 molecule would look like this. Remember that hydrogen is the exception to the octet rule. And the Lewis structure for the Cl2 molecule would look like this. All right, so these three molecules, these three Lewis structures represent covalent molecules, and each one has a single bond between the two atoms that are part of their structure. But we do see differences in these single bonds, and one of the ways we see differences is in the fact that the two electrons shared by the HCl molecule, by the hydrogen and chlorine in this molecule, these two electrons are not shared equally, as opposed to the two electrons in H2 and the two electrons in Cl2 are shared completely equally. So the electrons in a bond are shared. That is the point of covalent molecules. Drawing Lewis structures, you're representing shared electrons. But the sharing is not necessarily an equal game. Now, if the electrons are being shared by two identical atoms, then of course they're going to be shared equally. But if the two electrons in the bond are not shared by identical atoms, if they're two different atoms, there will not be equal sharing. And it depends how unequal it is and what the unequality consists of. That depends on quantities, physical properties of each of the atoms. And the physical property that we're looking at is something called electronegativity. Electronegativity is defined as the ability of an atom to pull electrons toward itself in a covalent bond. It is the ability of an atom to attract those electrons to itself or pull them to itself as it shares those electrons in a bond. So electronegativity is a property used to measure what's happening to an atom when it's in a bond, a shared bond with someone. For that reason, we don't speak about the electronegativity of the metals too much. We can actually measure electronegativities for them, but they don't typically show up in shared bonds. So the electronegativities of the metals are actually very, very low. We have low electronegativities. I'll abbreviate electronegativity with an EN, because they're not going to be pulling electrons to themselves in a shared bond. In fact, the metals tend to form cations. The metals tend to give their electrons away to nonmetals. For that reason, we focus on the nonmetals, and that does include hydrogen, as we discuss the electronegativities and bond polarity. Whenever the electrons are not shared equally, we say that this is a polar bond. The bond is polar. There is a side to it that has electrons closer to it than the other. Remember that electrons are negatively charged, and so there is a side of this bond that is more negative than the other. One side of the bond is more negative, the other side is more positive, and that's where the word polar comes from. We have sort of those opposites. In bonds where the electrons are shared completely equally, we call those bonds nonpolar. A nonpolar bond is a bond where the electrons are shared completely equally. A polar bond is where the electrons are not shared completely equally. The property that distinguishes whether or not they are shared equally is called electronegativity, and what we see on the periodic table, if we look at trends, is we see an increase in electronegativity as we move toward fluorine. Fluorine is the most electronegative atom. Now, electronegativity is actually measured in numerical factors, and fluorine has the biggest number for its electronegativity. It used to be defined on a scale of 4. I've seen pictures recently where we've actually gone to 4.1 for fluorine as the scale has been tweaked. The scale gets tweaked because this is a measured experimental value, and as our techniques and equipment become more sophisticated, we can make more careful measurements, and so sometimes the numbers change a little bit. But the bottom line that you should remember is that fluorine is the most electronegative atom. It has the biggest electronegativity, which means it's going to pull electrons to itself more strongly than anyone else on the periodic table. The second most is oxygen, and the third most is nitrogen, and the fourth most, followed closely behind the third, is chlorine. And so we see this fluorine is the biggest electronegativity, oxygen is second, nitrogen is third, chlorine is fourth, and then anybody else on the periodic table is going to have a smaller electronegativity than these four, and you can figure out the relative strength by looking to see whether or not they are higher, lower, left, or right on the periodic table as you compare them. All right, hydrogen, which of course shows up over here, is about on the periodic table about where carbon is. So hydrogen sort of sneaks in on any scale around the same place as carbon. Hydrogen and carbon's electronegativities are actually very, very close to each other, which means even though it is technically a polar bond in the sense that they do not share completely equally, they almost share equally. And so for a lot of applications, we do consider a carbon-hydrogen bond to be nonpolar because they're so close in electronegativity. But if I'm comparing hydrogen and chlorine, let's look back at this example. Chlorine is the fourth most electronegative atom. He is more electronegative than anybody else on the periodic table except fluorine, oxygen, and nitrogen. So chlorine is more electronegative than hydrogen, which means chlorine is going to pull on the electrons more in this bond. There are several ways that we can represent that. If I bring my molecule down here, and I am just going to draw the bond between hydrogen and chlorine, I'm not going to bother to draw in as lone pairs, we would say that hydrogen has a partial positive charge, that's how I make that symbol, and chlorine has a partial negative charge because chlorine is pulling those shared electrons closer to itself. Another way to represent it is with one of these symbols, either above or below the molecule. I've put the plus over here near the hydrogen, and then the arrow is pointing toward chlorine. These symbols for partial positive and partial negative could be written off to the sides of each of these elements. That part doesn't matter. All right, so electronegativity is a measure of the atom's ability to pull an electron to itself that's being shared in bonds. It's a pair of electrons. Might be a couple of pairs if it's a double bond. We can talk about electronegativities of atoms that are around double bonds. But you must remember the trends. I would remember the four most electronegative atoms and then memorize the trends and then be able to predict in a particular bond who is more electronegative, which side will be partial positive, which side will be partial negative, and so on.